Okay, today's lesson is to teach you how to write or draw Lewis dot electron structures. And the electron dot diagram, Lewis electron dot diagram, is a powerful tool to give you insight on where the electrons are around the atom, and also how these electrons then partake in chemical bonding. And we'll show you a little bit more about that in another tutorial, but today's lesson is just to teach you how to write the electron dot diagrams for each individual element. Okay, so here are the procedures for writing a Lewis dot structure for an element. And it's fairly straightforward. Each element symbol is surrounded by dots representing valence electrons. And the key word here is valence electrons, right? Not all the electrons in the element are going to be used in the dot structures, just the valence ones. And we'll talk about where they are first. So we write the symbol, we determine the valence electrons, and I'll show you how to do that. Then we place them as dots around the symbol and pretend that there's a box around the symbol, and we're going to put the electrons around each side of the box. You don't need to draw the box, right? Each side only gets 2 electrons, or a max of 2 electrons, and one side gets the first 2 electrons. And I'll talk about why that is in a minute. And then we count around each one, pairing them up as we do it. So this is kind of familiar, right? As we go around the electrons, they're going to be, if you remember back from our electron configuration, we started with first filling an orbital and then pairing them up as we add more and more electrons. So this follows that same type of process. So the electrons that are called valence electrons are the outermost energy level, right? So they're the outermost energy level, and they can only be from the S and P sublevels. So there's only a maximum of 8 of them, right? No D electrons are in the valence electrons for this particular Lewis dot diagram things. The outer shell electrons are the front lines with the atoms that interact. So when the atom bonds, only the outer electrons are involved in bonding. None of the inner electrons are bonding. For example, oxygen. Oxygen only has 6 valence electrons, even though it has 8 electrons total. Remember that oxygen is 8, and then it has a mass of 16. We have 8 total protons, therefore in a neutral atom we have 8 total electrons. But the only ones that are involved in bonding are the outer 6. So that's these ones here, right? Because this orbital is buried, right? Remember from our energy level, right? There's the 1s, and then here's the 2s, and then we have the 2p here. And if you're not familiar with what this is, you should go back and review that, or just take it for my word that the s electrons in this case are the only ones available for bonding. So we need to make sure that we know that. That's the thing we have to drive home. There's only going to be a maximum of 8 total, right? So from any energy level, 8 total. It's just going to be the S and the P electrons. Okay, so we talked about valence electrons, the only ones being involved in bonding. And so let's look at where we can find them. And we only talked about for the Lewis dot diagram, for simplicity, it only involves the electrons in the S and P orbitals, right? So we need to find out where those are located on the periodic table. So we know that the S orbital is represented by this column here, these 2 columns here, and the P orbital is represented by these columns here. And so we can say that if it's just a S and P, so here's our S and here's our P, then we can say, well, let's count them, right? We know we have a total of a maximum amount of 8 allowed. So we just go by the columns, and our first column here that's where our 1, so this would be for this column. 2 would be for this column here, and then we have 3. You can do the rest all the way up to 8, right? And each one of these columns has that many valence electrons. So this column here, all the elements in this column here have 3. All the elements in this column here have 4 valence electrons, 5 valence electrons, 6, etc., etc. And so you're going to see that the Lewis dot diagram is going to look similar for a lot of these elements if they're in the same group. And we can get the number of valence electrons for each group by just looking above above the here. So this is going to be 1, this is going to be 1, 2, 3, 4, 5, 6, 7, and 8. And then here's the numbers here listed on the top. So just reading down the group, all these are going to have 2. You can just count from left to right. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now we've known where the valence electrons are. So we've done this step here. We've determined the number of valence electrons, and then we've written our chemical symbol. And so now we can start doing them, and then we place them as dots around the chemical symbol, and I'll show you how to do that in a second. And remember, we start do all these rules here. So let's look at a couple of them real quick on the next slide. Okay, so now that we've got to understand where the valence electrons are and what their number is, we can go and use them to do our dot diagrams. And if you follow the rules on the previous that I just told you about, you just take the number of valence electrons, and the first 2 are paired up, and then everything else is just done signaling until you start pairing them up again. What I mean by that, let's look at that real quick. So here's our first molecule, boron, and remember we said that boron has 3 valence electrons from our thing. So it has 1 p and 2 s's. So we start here, and here's our first one, and here's our second one. So this is going to represent our s electrons, s valence electrons, and then this is our last p or first only p electron. Now that's not to say you could write the electrons down here for the s, and then the p one would be this one here. It doesn't matter where this goes, right? It just matters that you have 3 around here and 2 of them are paired up. So there's no real there's no rationale to why you have to put them. You don't necessarily have to. What I'm saying is you don't have to necessarily put them where they're located here. You could put them down here. You could put them the 2 down here and then 1 here, or you could put 2 here and 1 here. It doesn't matter where you put them, as long as you have 2 paired up and a single one someplace else. And then the next one is, let's look at sulfur. So sulfur, we remember we have 6 valence electrons. So let's just write that as 6 valence. 6 valence electrons. And therefore, how you do this normally is you're going to count again. So here's our first electron, that's 1, and then 2. So this is going to represent our s electrons. Then when we start counting, instead of going 3, 4, we're going to go 3. And remember, we go around until we have to pair them up again. They're all singles until we start pairing up. So that's the 3rd one, that's the 5th one, and now we go back and make the 6th one. Right? So you can see how I did that. So the first 2 are paired, then we go to 3, then we go to 4, then we go to 5. So it's this, and then back to pairing them up again. Right? Now, all of these are available for bonding later on. So it doesn't matter that they're paired up or not. They're all valence electrons, and they can all be bonded to later on. So they have 6 valence electrons. All 6 are available for bonding. Now, as I mentioned previously, that elements in the same group are going to have the same valence number of valence electrons, and therefore their Lewis dot diagram is going to look exactly the same. It's just going to have a different element in the middle where the thing is. So let's look at real quick what aluminum is, right? Because aluminum is right below boron, and it also has 3 valence electrons. And as you can see here, when I draw the Lewis dot diagram for aluminum, we have 1, 2, 3. And in boron, we have 1, 2, 3, and these are paired as these do. And so the structure looks exactly the same. Now let's look at oxygen. And oxygen is just above sulfur, so it should have the same electron structure as sulfur does for the Lewis dot. So let's just look at them. So we have 1 electron here, that's good. 2 electrons, that's good. 3, 4, 5, and then we pair it up again, and that's 6. So again, it looks exactly the same as sulfur because it does have the same number of valence electrons, and we're only interested in the number of valence electrons. Okay, so what I'd like you to do here for practice is to do some of these ones here. I've listed several of these elements that you can write the Lewis dot diagram, and when you're finished writing them, we'll stop the video first, write them, and then come back and check your answers, and I'll have them all written up for you. Okay, so I've written in the the answers for all the things. So let's just quickly review these real quick. So remember, sodium is group 1, so it only has one valence electron, and so there's my 1 electron. Nitrogen is in group 5, and therefore it has 5 valence electrons, and you can count them here. There's 5 there. Calcium is in group 2, so it has group 2 electrons. And silicon, right below carbon, has 4 valence electrons, and you can count them here. And then neon, which is a noble gas, its whole electron shell is filled, so it should have the max of 8 electrons. So we have 8 electrons here. We have 4 here, 1 here. These are only valence, remember that. 5, and then 2. And their last one is bromine, and bromine is a halogen, and it's always going to have 7 electrons. And you can count them here. There's a spot here. There's an empty spot here for another electron. So if you've got this, you're good to go. It shouldn't be any more complicated than that. And then the next lesson will show you how to use these to find out where the electrons are in chemical bonds.